Okay, this lecture is going to guide you through the exercise G. First, the reading on page 73. What is the notation for the inverse function of f of x? Well, the inverse function is the function that undoes whatever f of x does, and the way you write it is f of to the negative 1 of x. Man, that's terrible writing, huh? This pen is not very good. There we go, that's better. Okay, is 1 of f of x the inverse function of x? No, it's not. It looks like f to the negative 1x might be equal to 1 over f of x, because that's usually what we do with exponents. But actually, this is not an exponent. It's just a notation that means inverse, so don't make the mistake of thinking that that's true. Okay? How can we make sure that an inverse function is also a function? Well, you make sure an inverse function is a function the same way you make sure functions are functions. You use a test, such as the vertical line test. You know, you have a function, and you draw a vertical line through it at any point, and it only crosses the function at one point, and then you know it's a function, right? If you have something like this, and you cross through it, and whoops, that hits it 3 times, so that is not a function, for example. The other way you could say it is, hey, if it's a function, if I choose an x here, then there is only one y which the x maps to. So I choose an x here, yeah, there's only one value, x here, only one y value, right? Okay. So that's how we do it with like the vertical line test, for example. Vertical line test. Graphically, how would you find the inverse of a function? How would you reflect it? Well, if you read the reading, you will see that if you have a function like this, okay, you will see that the inverse function is actually a reflection of this function along the diagonal axis. So I'll draw the diagonal axis here. Okay, so if you reflect a function about the diagonal axis, then it will be the inverse of the function. So let's say that this is f. This here is f of negative 1. Okay? So you reflect it. You reflect it about the diagonal axis, which is y equals x. Okay? If f of negative 1x is the inverse of f of x, then what is f follows f of negative 1 of x equal to? Well, part of the definition of an inverse function is that it undoes a regular function. So if we put it as a composite with the regular function, then you just get back the same value you started out with. Okay? And then I ask, what about f of negative 1 follows f? And it's just the opposite of that, and guess what? It also gives you the original value. Okay. Think back to Mr. Tsubaki's magic trick where I asked you to perform in sequence the functions a of x equals 2x, b of x equals x plus 4, c of x equals x divided by 2, d of x equals x plus 4, and e of x equals 2x. Draw the 5 functions as 5 connected function machines with input x and the output. Oh my gosh. Looks terrible, doesn't it? Okay. So, a function machine is a little box that has an input and an output, and the box does some kind of math operation. Okay? So remember when I did the magic trick. First thing I did, I asked you to take a number and do 5 operations on it and see what you get at the end. Okay? So all these function machines are cascaded one to the other, and the first input you're going to give it is a number, let's say x, and then the first function machine box is going to multiply by 2, and the next box is going to add 4, and the next box is going to divide by 2, and the next box is going to add 4, and the next box is going to multiply by 2. And if you want to, you could name the function boxes A, B, C, D, and E. So we just drew the 5 function boxes. The input is x. The output of this function box times 2 would be 2x. The output of this function box would be 2x plus 4. The output of this function box would be 2x plus 4 divided by 2. The output of this function box would be 2x plus 4 divided by 2 plus 4. And now we can start simplifying a little bit, like 2x plus 4 divided by 2 is actually x plus 2 and then plus 4, right? Do you see how that simplifies? So, and then if we multiply that by 2, that's actually x plus 6, right? Okay. Then if we multiply x plus 6 by 2, that's equal to 2x plus 12. Okay? So we just took these 5 functions, and then we combined them in a composite function simplified to 2x plus 12. So, when I say express the function as express the 5 functions as a simplified equation for one composite function m of x, I could just put 2x plus 12, right? Because when I cascade all these functions together, I start with x, what comes out? 2x plus 12. It was much more complicated, but I just simplified it, right? Okay? So instead of like doing all these separate steps, I could just take whatever input, let's say my input is 2, and I could just plug it directly in here. It's the same thing as going through these 5 functions separately. Okay? Page 74. Show how to find the inverse function of m of x using variable interchange. Okay, remember variable interchange? So if we have y equals 2x plus 12, which is the composite function, to figure out what the inverse function of this, you remember in the magic trick how I would guess what your number was just by thinking in my head for a little bit? What I would do is I would use the inverse function to do that. Well, what is the inverse function? The inverse function you find by changing the y to x, and you change the x to y, and you leave everything else the same. Because what you're doing when you do the inverse function is you're making the input the output and the output the input. The input here is x, the output is y, and we want to switch the input and output. So we change x to y, which is what we normally call the output. We change y to x, which is what we normally call the input. And now we just need to isolate y so that the answer is in y equals something something, and then we will have a function which does the exact opposite of what you did on your paper, I'm going to do in my brain. Okay, so how do we do that? Well, first we're going to subtract 12 from both sides, and we're going to get x minus 12 equals 2y. And then I'm going to solve for y by dividing both sides by 2. And then I'll have y equals x minus 12 divided by 2. So this is what I was doing in my head. Whenever you gave me a number, like if you gave me the number 46, I would put 46 in here. I would subtract 12. That would give me 34. I would divide by 2, and I would get 17. And that was the number you started out with, for example. Let's try that out. You start out thinking 17. Then you multiply it times 2, you get 34. And then you add 12, and you get 46. And then you say, Mr. Tsubaki, my second number is 46. Figure out my first number. Then I take 46, I subtract 12, I get 34, I divide by 2, and I get 17. I say, is your number 17? And he said, why, yes, it is. Okay. So that's how you find a inverse function using variable interchange. You change the x to y, you change the y to x, and then you solve for y. Give an example of a self-inverse function. Why is it a self-inverse function? Well, a self-inverse function is when a function and its inverse are the same. Okay? So let's give an example of that. For example, y equals 1 over x. Y equals 1 over x is an inverse function because let's say you start out with 2 and then you put it in this function. What do you get out? 1/2. What if you put it through again? You put 1/2 in, and then what do you get out? You get 2. So if you put it through the function twice, you get itself back. Okay, so that is a self-inverse function, a function which is its own inverse. Okay, now what is a characteristic of self-inverse functions? Well, if you start drawing a bunch of self-inverse functions, you're going to see that there's something common between them. For example, the self-inverse function I just drew, y equals 1 over x, looks like this. Okay? Let's draw some other self-inverse functions. And you don't know these are self-inverse functions, but I'm going to tell you that they are. That's a self-inverse function. That's a self-inverse function. Oops. That's a self-inverse function. Do you see anything common between these? Okay, in terms of symmetry, where is the axis of symmetry for these? Here. Well, there's also one here, but the only axis of symmetry that's common between all of these is this one. Okay? So, this diagonal axis is an axis of symmetry for every single one, and that is the characteristic of a self-inverse function. Okay? So, we're going to see that later when we do these problems. Now I'm going to do one of these problems just so that you can see how you do. Okay. So, for each of the following functions f on the same set of axes, graph y equals x. So we'll graph y equals x is that diagonal line I was talking about. And the function and its inverse. Okay. And then we're going to find f of the inverse function using some other method. Okay? Okay, so first of all, we're going to find the inverse function graphically. So we're going to graph the function, 3x plus 1. And if you remember, to graph 3x plus 1, that's the gradient, or the slope, and that is the y-intercept. In IB land, they call the slope gradient. Okay, so there's the y-intercept, plus 1. And the gradient is 3, so that means rise is 3, run is 1. Rise is 3, run is 1. Do you see that? Okay, so the gradient is like that. Kind of like that. That's not a very straight line, is it? Okay, so that's my line. What do you think the inverse looks like? Well, the inverse function is going to be the reflection of this line over this diagonal axis. And so, like, this is going to be a common point, but the rest of it is just going to be like a mirror image over that line. And see if we can draw that. Okay, so instead of the rise over run 3 over 1, it's going to be 1 over 3. So do you see how the green is a reflection of the red over the axis blue? Okay, so that's how that works. That's how you find the inverse function using a graph, okay, and which is the first thing they asked us to do, using coordinate geometry. Well, actually, they, yeah, okay. And then now we're going to use variable interchange. So if we know that the function is that, then first thing we're going to do is going to switch the variables. We'll get x equals 3y plus 1. And then we're going to use algebra and isolate the y by itself right there. Okay, so first thing we're going to do is subtract 1 from both sides. That'll be x minus 1 equals 3y. Then we're going to divide both sides by 3. That'll be y equals x minus 1 divided by 3. Okay? So we have just found the inverse function using variable interchange. Okay? And you do not need to use the coordinate geometry approach, which is to take the gradient and invert it, and you don't have to do that. You can just use variable interchange and then use the graphing method. Okay?